And there's a starter question, or a couple questions to begin with. And it says, an identity is a blank equation. We already learned what an identity was in chapter 1. Anybody want to remind us what an identity is? Marcos? Marcos has got a coy smile on his face, not wanting to answer. It's a true equation. Okay? It's an equation that's true wherever each side is defined, technically speaking. But for our purposes, it's a true equation. All right? And then the 6 reciprocal identities that we learned in chapter 1. So we figured out that the sine of x was 1 over the cosecant of x. The cosine of x is 1 over the secant of x. The tangent of x is 1 over the cotangent of x. And then I just write each one of those kind of in reverse. So the cosecant is 1 over the sine. The secant is 1 over the cosine. And the cotangent is 1 over the tangent. Now, I'm saying 1 over tangent, but I'm writing cotangent of x equals 1 over tangent of x. Okay, again, a trig function doesn't mean anything unless you plug an argument into it, plug an angle into it. Okay? And then the next one says, how can we write tangent in terms of sines and cosines? This was on all of these were on the first test, weren't they? You had to have these memorized. So tangent of x is equal to the sine of x over the cosine of x. And then if we're going to write down cotangent, and we remember that these are reciprocals of each other, it's going to be the cosine of x over the sine of x. And then this is a really important identity. It's called the fundamental trig identity, or we gave it another name, and I usually call it by its other name. I call it the Pythagorean identity, and that is... What is it? The power of x. Sine squared of x. So if you take the sine and square it, plus cosine squared x. Take the cosine and square it. We say sine squared x plus cosine squared x. That equals 1. Okay, that's the fundamental trig identity, or that's the Pythagorean identity. And then there are a couple others that we can derive directly from that. And what we do here is we say, well, let's see. If I've got this relationship that sine over cosine is a tangent, let's divide everything here by a cosine squared. So I'm going to write this. Don't write this down. I'm going to divide this by cosine squared x, that by cosine squared x, and that by cosine squared x. Okay? Well, sine squared over cosine squared. Sine over cosine is tangent. So sine squared over cosine squared would be tangent squared of x. What's cosine squared over cosine squared? 1. Very good. And then 1 over cosine squared. 1 over cosine is secant, so this is going to be secant squared x. Okay? So this is the Pythagorean identity, the fundamental trig identity. This is one that can be derived directly from that. Questions? Yeah.
So why do you always have to divide by the cosine?
You don't always have to do that, okay? I'm just saying you... Sure, we're going to do that next, actually. Okay? So does everybody understand, if this is a true equation, if this fundamental trig identity is true, if I divide both sides by cosine squared, it produces this identity, and that it therefore would also be true. Does that make sense? Okay? So let's go through here, and the question is, well, what if I don't want to divide by cosine? What if I want to divide by sine? So let's divide by sine squared, sine squared, sine squared. Well, sine squared over sine squared, that means this first one's going to be a 1. Cosine squared over sine squared. Cosine over sine is cotangent, so this would be cotangent squared, and then 1 over sine squared is going to be cosecant squared. Okay? So I'm now going to erase those. This is how we derived it, but I don't need those anymore. Okay? I would have this one memorized. Absolutely. Should have had that memorized for the last test. This one right here, I mean, here's what I'd know about the two of these. If you have these other ones memorized, you're just going to be able to do some problems more quickly. Okay? If nothing else, you should know, okay, I can quickly take this and I can turn it into that. You should know that tangent goes with secant and cotangent goes with cosecant. Now, how you keep those straight, which one's on which side and all that sort of stuff, fine with me. I kind of keep them straight this way. This is a tangent, this is a secant. They don't have the words co in front of them. This is cotangent. It goes with cosecant. That's one way I keep them straight. And then I also think, well, which one goes on which side? Well, if these are sines and cosines over here, I'm only going to be able to have something with sines and cosines here. Tangent is made of sines and cosines. So is cotangent. Okay? So if I remember, I've got tangent with secant. Tangent squared plus 1 equals secant squared. If I remember, if I've got a cotangent, that's going to go with cosecant. So 1 plus cotangent squared equals cosecant squared. Okay? Don't care how you remember them. Got to have this one memorized. Need to know those two. Need to memorize those or be able to derive them in about 5 seconds. No more than that. Okay? More things that if you just know them down cold, you're going to be in much better shape later on. Okay, are there any questions there? Okay, so we've seen all those before, right? Okay, just a good reminder. So this section is about basic identities, okay? Kind of reintroducing those, and we're going to do a couple different things with those. The stuff that we've gone with up above here, those are the building blocks for everything that we're going to do in Chapter 3. In fact, we're going to take those and we're going to build new identities from those, okay? So it'll be kind of interesting, but the good part about this is, yeah, they can help you in calculus and all that sort of stuff, but identities really, they stretch your brain a little bit. They teach you how to think in a different way or operate in a different way. So here are some of the things that we're going to work on. Okay, it's going to help you think more logically about different types of problems. It's going to allow us to do this, and this is kind of a common theme in math. It's going to allow us to take something that looks unfamiliar, looks really hard and complicated, and we're going to make it look more familiar using identities. And then the last thing is use tools that we that we have to solve problems that if we looked at it to begin with, think there's no way, can't do it. It's impossible. But we're going to use all the tools that we've got, the algebra that we know, the arithmetic that we know, the unit circle that we know, okay, and these identities that we already know, we're going to use those to solve really complicated problems, okay? So the first thing I want to point out is that because sine and cosine are the functions that are most familiar, they are really the building blocks for all the other trig functions. A lot of times it's useful to rewrite expressions in terms of sines and cosines. Okay? So it says write the following expression using only one trig function. It doesn't say which, but it wants you to only use one trig function. Okay? Now there can be other numbers in there, but only one trig function. Okay? You actually have problems that ask you to do stuff like this. So I'm fine with the 1. There's not really much I can do with the 1. Okay? Sine, well, I could look up here through my list here or think about this. I could make that a cosecant. But what I really ought to hone in on is if you ever see a trig function squared, and I'm going to say this numerous times, so please don't misquote me. If you see a trig function squared, that is your hint that it might be, not is, but might be, able to be simplified using a Pythagorean identity. So if you see a trig function squared, you think, hey, wait a minute. I know the Pythagorean identities, these three guys right here. How could I replace cosine squared with something else so that this maybe is in terms of one single trig function? So let's take this one right here. If I have sine squared x plus cosine squared x equals 1, could I solve that for cosine squared? What could I do, Marcos? Subtract sine squared x. So here's what I've got. I've got cosine squared x equals 1 minus sine squared x. And this is back to one of the first things that you learned how to do in algebra, and that was substitute or plug things in. Wherever an expression asks for a cosine x, or excuse me, cosine squared x, we can put a 1 minus sine squared x. So instead of writing cosine squared x here, I'm going to write 1 minus sine squared x plus sine of x plus 1. So have I written this in terms of one trig function? Yes, I have. The only trig function that shows up in here is sine, and I ought to clean this up just a little bit. Yeah.
Can you put parentheses around it since you're substituting it in?
If you want to put parentheses around it, that would be fine. Excellent point. I normally try and plug in parentheses. Is that going to make a difference on this one? Yep, it's going to be this stuff plus this stuff. There's no multiplication or division or anything, so I can be a little bit loose with that, but thank you for calling me on that. I then am going to add all these together. So what I could do is I could say, you know what, I'm going to put the 1 and the 1 together. That's going to be a 2. I'm going to write the sine of x here, and then I'm going to write minus sine squared of x. Now, it only says write it in terms of one trig function. Now, that doesn't mean you can't have numbers in there. So is that written in terms of one single trig function? It is. We'd be done with the instructions at that point. We'd be finished. So the weird part about some of these problems is your answer isn't a number. You're not going to get a graph. You're not going to get pi force as the answer, or radical 3 over 2 is the ratio for the answer. You're going to get another just trigonometric expression. Okay? That's it. Now, could you have written this negative sine squared x plus sine x plus 2? Could you have written it in the other order, in kind of descending order? Sure. Either way is fine. Okay? As long as you've got those same three terms. Any questions? Okay. So let's take a look at the next set of problems. It says simplify the following trigonometric expressions by writing in terms of sine and cosine. This is a really good skill, writing in terms of sines and cosines. It's not that you always do this, but it's one of the things that makes, in many problems, makes them easier to work with. So we're going to take this and we're going to write everything in terms of sines and cosines. So I'm going to kind of zoom in on this guy right here. This is already written in terms of sines. This is not. So I'm going to write 1 over sine squared of x minus, how can I write tangent in terms of sine and cosine? Yep. So this is going to be sine over cosine, or sine squared over cosine squared. This technically is what we call a complex fraction. I never divide by a fraction, so I'm going to take this and I'm going to flip it over and I'm going to multiply. So this is going to be cosine squared on the top and sine squared on the bottom. So here's what I've got. I've got 1 over sine squared of x minus cosine squared of x over sine squared of x. Now, I've successfully written it in terms of sines and cosines, but the instructions say to simplify. So is this as simple as I can write that? It's not. I've got two fractions. They already have a common denominator, so I'm going to write 1 minus cosine squared of x over sine squared of x. Is that as simple as I can write it? What? Marcos says no. Anybody else say no? Marcos, tell us why you say no.
So when you subtract cosine squared x from the identity, it's sine squared equals 1 minus cosine squared x, so then it's just sine squared x over sine squared x, so it just equals 1.
Now you all followed that, right? Okay, here's what he said. Let's come back up here, and I'm going to write this in blue. Instead of solving this one for cosine squared, instead of moving the sine squared to the other side, I'm going to take this and I'm going to move the cosine squared to the other side. That's going to give me sine squared x equals 1 minus cosine squared x. If this is a true identity right here, that's a true identity right there. Everybody agree? So wherever you see a 1 minus cosine squared, what can we put in its place? We can put a sine squared x. So on the top, I'm going to put a sine squared x. On the bottom, I still have a sine squared x, and we get the surprising result for simplifying this. From this ugly mess right here, if I change it and write it in terms of sines and cosines and I simplify, what do I get? 1. Doesn't get much simpler than that. Okay, questions? Okay, can I slide this over? Okay, let's take a look at the next one. Again, simplify by writing in terms of sines and cosines. So look at this. We've got a 1, we've got a cosine, a tangent, a cosecant. Cosecants aren't our favorite. And then I've got a cosecant squared on the bottom. Okay, maybe I shouldn't be prejudiced. Cosecant isn't my favorite. Okay, can I cancel the cosecant with the cosecant? Somebody tell me why not. You've got, okay, this cosecant is part of a term. It is not a single factor. If this one had a cosecant in it and we could pull out a cosecant so that it was a factor, we could cancel it. Don't cancel terms or parts of terms. You cancel factors. Okay? Besides that, we haven't even done what it said. It said do this by writing in terms of sines and cosines. So I'm going to take this and I'm going to write 1 plus, this is the cosine of alpha. Tangent is sine of alpha over cosine of alpha. And cosecant is 1 over sine of alpha. And on the bottom I have 1 over sine of alpha. Now, what I've done here is just blindly gone through, followed the instructions, wrote everything in terms of sines and cosines.
Alright, we're done.
It looks messier, but we are really close to done, aren't we? Because if you take a look at this, since everything else is a fraction, I'm going to think of cosine of alpha as a fraction, put it over 1. I can cancel the factor of cosine alpha with cosine alpha. I can cancel the factor of sine alpha with sine alpha. So that means on the numerator, I only have, well, this is a 1, and this is now a 1. So what's on the top? 1 plus, careful, careful.
1.
That's a 1, that's a 1. What's on the top?
2.
A 2 over 1 over sine of alpha. Now I'm not done because this is a complex fraction. What do I do with the complex fraction? Take the bottom, flip it over, and multiply. So I'm going to cross this off. I'm going to multiply by sine of alpha over 1. Don't even need to write the 1, do I? So if I take 2 over 1 times sine alpha over 1, my answer on this particular problem is 2 sine of alpha. So from this ugly mess right here, write it in terms of sines and cosines, do some algebraic simplification for the most part. We're just working with fractions, properties of fractions, complex fractions, stuff like that. We get it simplified to the point where that mess turns into just plain old 2 sine alpha, okay, which is much, much better, right? Any questions? Okay, so I'm going to do this next problem. Now, if you want to write this one down, you can. You don't have to, okay? But I do want you to think about this. It's always good to have more than one way to solve a problem. Now, we already know that the tangent of pi fourths is 1. Okay, we've done that several times. We think of the unit circle, 45, 45, 90. The two legs are the same, so the opposite over the adjacent would be same number over same number, so that's going to be a 1. Okay? But sometimes solving a simple problem like this in a very complex way gives us some tools that we can use on more complicated problems that don't have a simple approach. Okay, so just bear with me here. It says, use the identity tangent x equals sine over cosine. Okay, so we've got this guy right here. And it says, solve the Pythagorean identity for cosine and then substitute the resulting expression into the identity in part A above. So let's go to there, right to that comma. Take the Pythagorean identity and solve it for cosine. So I'm going to do some work up here. So it's sine squared x plus cosine squared x equals 1. It says solve for cosine. So we already did this up above. Cosine squared of x equals 1 minus sine squared of x, right? Now am I done per those instructions? Solve the Pythagorean identity for cosine of x. Have I done that?
No.
Not quite, because I've got cosine squared. They said just get plain old cosine, right? So if I want plain old cosine, I'd have to take the square root of both sides, right? So I get the square root of 1 minus sine squared of x. Now, when we put a square root in a problem, what do we normally have to put?
Plus or minus.
Plus or minus. Okay? So I normally put a plus or minus here. So I'm going to come down here, and then it says, substitute the resulting expression into the identity in part A above. So this says that the tangent of x is equal to sine of x over, what am I putting in for cosine? That ugly mess right there. So I'm going to put plus or minus. My gosh, why would anyone want to do this? Okay, follow along. If this is a true identity, and that's a true identity, then that's true and that's true, which means when I make this substitution in here, this should be a true identity. It should work, right? Any questions there? Okay, now, do I need to worry about the plus or minus on this particular problem? The answer to that is no, I don't. I can assume it's the positive one because we're in quadrant 1. And what do we know about all the trig functions in quadrant 1? They're all positive. Okay? So is everybody okay if I don't put the plus or minus there? Okay, I'm in quadrant 1. We know the answer is going to work out to be positive. Okay, I could leave it and then just make sure the number works out to be positive at the end if we wanted to. Any questions there? Okay, so this says that the tangent of pi fourths should be the sine of pi fourths over the square root of 1 minus the sine of, now I'm going to write it like this. Everybody watch, please. Sine squared of x literally means find the sine of whatever you're plugging in and then square that. Okay? Now, what is the sine of pi fourths? It's the y coordinate on a 45, 45, 90. Square root of 2 over 2. Okay, so here's what I get. Square root of 2 over 2 over square root, and this is going to look ugly for a second, 1 minus square root of 2 over 2 squared. Now stop and think for just a minute. We already know what the answer should be. The answer had better work out to be 1. Doesn't really look like a 1 right now, does it? But let's check and see. Square root of 2 over 2 over square root 1 minus, if I square the square root of 2, I get 2. And if I square 2, I get 4. So this is the square root of 2 over 2 over the square root of, well, this would be 1 minus 2 fourths, or 1 minus a half, so that's going to be a half. And then I've got this nice property of radicals. So a lot of people don't like fractions, but fractions are actually really easy to work with in many situations. This would be the square root of 1, which is 1, over the square root of 2. So now this is a complex fraction. We take the bottom, we flip it over, and we multiply. That would be radical 2 over 1. Now take a good look at this. Because when I multiply the two of these together, I get radical 2 times radical 2 on the top, and I get 2 times 1 on the bottom. And what's my answer? My answer is 1. Just like we knew it would be. Now that's a wild way to do that particular problem. And no one would ever do that. No one would ever compute the tangent of pi fourths using that technique. But the fact that we used some identities to arrive at exactly the same answer as this simple expression right here should be kind of cool and should be a little bit of evidence that, gosh, did we do everything right? And do these identities actually work? Are they really true equations? Absolutely. Okay, does that make sense? Okay. Any questions? Okay, let's take a look at the bottom of this page then. And then let's remind ourselves of what odd and even functions are. So, even, pardon me, even functions are symmetric with, what is it, Marcos? It is the y-axis. Even functions are symmetric with the y-axis. Okay, now careful here because this screws some people up. Odd functions are symmetric with the, thank you very much, good answer. The answer is origin. It is not x-axis. If it were symmetric with the x-axis, you wouldn't have a function. Okay? So let's come over here. I've got two examples. Okay? So you can think of this one as x squared and you can think of this one as x cubed if you want to. This one is symmetric with the y-axis. What we mean by that, and the little test that you would have learned when you were learning about odd and even functions is, if you plug in a negative x, you get exactly the same thing as if you plugged in an x. So if we looked at this graphically, what even means is, it doesn't matter whether you go to the left or the right, you get exactly the same function value. If you went up to 5 here, when you went over to whatever x was, if you go over to negative x, you'd go up to that same function value. So it doesn't matter whether you go to the left or the right, you get the exact same function value. Now odd is a little bit different. If I go over here and I get f of x, let's say I go over to 2. That means I'd have 8 on the graph, right? 2 cubed is 8. What happens if I go over to negative 2? Negative 2 cubed is negative times a negative times a negative. That would be negative, but it's also 8. Okay? So what happens here is if I go to the right, I get the exact opposite of what I get if I go to the left. Instead of getting the same thing on either side, I get the exact same number, but opposite sign. Okay? And that's symmetric about the origin. You could take the graph, spin it around the origin, and the shape would look the same, basically. Okay? So let's think about the functions that we've been dealing with, and let's narrow in on the two that we're most familiar with, so sine and cosine. So sine looks like this. Okay? And cosine looks like this. So if this is cosine of x and this is sine of x, and these are really crappy graphs, and you had to say they were symmetric with something, cosine is symmetric with the y-axis. If you go to the left and the right, look, if you go over here to pi halves, you get the same thing as if you went to negative pi halves. So this one is even. Cosine is an even function. Okay? What about sine? If I go over here to pi halves, I get 1. If I go to negative pi halves, I get 1, but it's negative. So this is odd. Okay? Now back up here are the technical definitions. Okay? If it's even, f of negative x is the same as f of x. So you can kind of ignore the negative on the number that you plugged in. For odd, it means that f of negative x is the negative of f of x. Same number, just exact opposite sign. Okay? So let's come back over here and let's talk about, these are called the odd-even identities, and I would know these. They come in handy. You're going to see them on today's assignment. So because sine is odd, the sine of negative x is the negative of sine of x. It's kind of like pulling the negative out front and kind of simplifying the angle that we're using. Cosine is even. So if you go to negative x, you get exactly the same thing as if you just plugged in a plain old x. So sine is odd, cosine is even. Think about tangent. Is tangent odd or even? Odd. So tangent of negative x is negative tangent of x. Now here's the cool part. The only one that's even is cosine. So if cosine is even, its reciprocal should also be even. And if you think about the secant graph, it is symmetric about the y-axis. So the secant of negative x is same as the secant of x. Cosecant is odd, just like its reciprocal function. So this would be negative cosecant of x. And cotangent is odd, just like its reciprocal. So this is going to be negative cotangent of x. And then just a couple simple problems. Rewrite each trig function using the odd and even identities. So the sine of negative pi thirds is exactly the same as, it's kind of like, this isn't technically what's happening, but it's the net effect. Pull the negative out front.
That's it.
Yep. Now, does it say evaluate? Does it say tell me what the sine of negative pi thirds is? No, it doesn't. Okay? But we do know they're the same. And then I've got the cosine of negative 135. If we rewrite that, that is exactly the same as the cosine of 135. You can just lose the negative there. So with even functions, you can lose the sign. With odd functions, pull it out front. Again, that's not technically what happens, but that's the net effect. Okay, are there any questions there? Sure? Okay, if we have time, I'd like to come back and take a look at this in terms of the unit circle and just double check and see if we got those right. Okay, so the point of this chapter, a lot of what we're going to be doing is we're going to be taking the identities that we already know, producing new identities, or verifying that they're going to show us something and we're going to show, gosh, you know what, that's actually true. Okay? And we're going to use a lot of the algebra that we already know, a lot of work with fractions, properties of fractions, and a lot of the basic identities. Okay? So keep in mind that we're going to work with factors and complex fractions quite a bit. So this one says simplify each expression. And again, this doesn't always work, but many times a good place to start is writing everything in terms of sines and cosines, because those are really familiar and nice functions. So to simplify this expression right here, I'm going to take this and I'm going to write it in terms of sines and cosines. So the top is cotangent. This is why you've got to have them memorized just on the flyleaf of your brain. cosine of x over the sine of x. Cosecant, 1 over sine of x. Any questions there? It's an algebra problem now. Complex fraction, flip that over and multiply. So this is going to be the sine of x over 1. I have two common factors there, sine of x and sine of x. So what is my final answer to this problem? Cosine of x. That's it. That's all there is to it. Good? Okay. Let's take a look at this one. Again, we want to write this as simply as possible. Does anybody recognize this pattern? Secant minus 1, secant plus 1. We're getting there. I'm thinking in terms of algebra. Like a minus b. Has a name. The middle term's gone. It's called a difference of squares. Okay. We could also say that these are conjugates of one another. So when I multiply these together, here's what happens. I get a secant squared of x. When I multiply here and here, I get a secant of x. When I multiply the negative 1 through, I get a minus secant of x, and then I get a minus 1. Those middle terms, again, it's just algebra at this point. I get a 0 for the two of those. They cancel to be 0. And then I have secant squared of x minus 1. Now, that looks like a pretty simple answer. Could I rewrite it? Close. No. Okay, remember what I said? If you see a trig function squared, that's your hint that it might be able to be simplified using a Pythagorean identity. So go back and look at the three of those. By the way, without looking, which one goes with secant? Sine and cosine go together. Tangent and secant go together. Cotangent and cosecant go together. This is going to be something to do with a tangent. So remember, it's tangent squared plus 1 equals secant squared. So if I move the 1 to the other side, tangent squared of x equals secant squared of x minus 1. So wherever there's a 1 minus secant, or excuse me, secant squared minus 1, what can I put in its place? Tangent squared of x. That right there is the simplified answer. Okay? Now, I do want to draw your attention to this right here. Please keep in mind, and this is one thing that frustrates students about trigonometry, in particular the identities that we work with. If it says simplify, pardon me, or if it says verify an identity, there may be a dozen different ways to do it. So you're going to do it one way. You're going to look at your neighbor and you're going to say, my gosh, I don't have any idea what you did. Okay? As long as you both did it correctly and got to the same place, it doesn't matter. Okay? And keep in mind that there are different ways of simplifying. Somebody might say, you know what, that's simple enough. Okay? The way I usually say this is, if you had to use it again, which one would you rather use? This one or this one? I'd probably want to use the second one because it's easier. It's just one expression. Okay? So that's how you know you've simplified enough. Okay, then it says, rewrite each expression in terms of the indicated trig function. So we want to write cotangent in terms of cosecant. I want to start with a cotangent and I want to turn it into a cosecant. So only cosecant. Can you think of any of the identities that involve the two of these? Didn't we just get done saying, isn't there a Pythagorean identity that relates cotangent and cosecant? So, and that is 1 plus cotangent squared of x equals cosecant squared of x. That's the starting point. And I want to write cotangent in terms of cosecant. So in other words, take this and solve it for cotangent. Get cotangent all by itself. So I'm going to move the 1. Cotangent squared of x equals cosecant squared of x minus 1. How do I get cotangent by itself? Square root. Now, I don't know which quadrant I'm plugging into, so I do need the plus or minus. So cotangent in terms of cosecant would be, cosecant squared x minus 1 underneath the radical. That right there is what they're after. Any questions there? Yeah.
I got really lost from
Okay, this is a Pythagorean identity from the front page.
Yeah.
And it says write cotangent in terms of cosine, or cosecant. So we want to have cotangent on one side all by itself, and everything else on the other side either needs to be numbers or cosecants. So I take this one, which we already know is true. I move the 1 over. That gives me cotangent squared over here by itself, but I don't want cotangent squared. What do we want? We want just a plain old cotangent. So how do I undo squaring? Take the square root of both sides. That's it. Seems a little bit weird. Okay. Again, it's mental exercise. It's kind of working out some skills that you haven't worked on before. Okay. Questions there? Okay. Write sine in terms of cotangent. Sine in terms of cotangent. So you've got to have sine on one side and cotangent on the other side. These can, in my opinion, these are the toughest ones on the assignment. So let me give you a hint. Watch. Everybody watching? 1 plus cotangent squared of x equals cosecant squared of x. Now, I would like an expression that only has sines and cotangents in it. This has cotangent. What is this? What's cosecant squared? Can you rewrite that? Isn't that 1 over sine squared? So I'm going to write 1 plus cotangent squared of x equals 1 over sine squared of x. Again, watch the algebra. This is usually what people struggle with. They can say, oh, well, I know what I'm supposed to do, but I'm stuck. I don't know how to get there. I want to get sine on one side completely by itself. So I'm going to think of this as a proportion. I'm going to multiply together here and multiply together here. So this is going to be sine squared of x, 1 plus cotangent squared of x equals 1. How do I get the sine by itself? Let's get rid of this mess right here. Let's divide both sides by that. So this is going to be sine squared of x equals 1 over 1 plus cotangent squared of x. And remember, we wanted sine all by itself. Is it by itself right now? We have the square sitting there. How do I get rid of a square? Take the square root. Okay. Now on this particular one, this doesn't happen very often, so I'm going to go ahead and leave it like this. This would be plus or minus big square root 1 over 1 plus cotangent squared of x. Okay, I'm fine if you left it that way. Again, that doesn't happen very often. Okay, are there any questions? Kind of a wild problem. Again, there's no number answer here. Your answer is just another identity. It's another formula that relates to trig functions. Okay. Good? Okay. Let's quickly do these next couple. It says, use identities to find the exact values of the other 5 trig functions if tangent of alpha is 3 over 4. And let's see, alpha is in, well, what's good about this? You don't have to worry about any of the pluses or minuses. You know they're all going to be positive, right? Now, we could draw a picture for this. We could draw a little triangle in this quadrant. We could say the opposite is 3 and the adjacent is 4, and we could find this one right here. But it said use identities. So if we know that the tangent of alpha is 3/4, we can immediately know its reciprocal. What's the reciprocal of tangent? So tangent of alpha would be 4/3. So there's one. There's the one they gave us. Here's another one. Okay, now if we're going to find the other ones using identities, again, let's go with what we started with. Go back and think about those Pythagorean identities. So tangent squared of x plus 1 equals secant squared of x, right? How many variables are there in this problem? I'll give you a hint. I'm pointing at them. There's only 2. And we know this one. So this is 3/4 quantity squared plus 1 equals secant squared of x. We good there? So this is let's see, 9 over 16 plus 1 equals secant squared. If I get a common denominator, that's going to give me 25 over 16 equals secant squared. I don't want secant squared. What do I want? Really, we've asked this a couple times now. We just want secant, right? I don't want the square. So I take a square root. So that means the secant of x is 5 on the top, 4 on the bottom. Now, that's what secant is. If you know secant, what's the easiest one to find from secant? It's reciprocal cosine. So the cosine of x would be 4 over 5. Okay? I now have 4 of the 6. All I need to do is find the last one. And to do that one, I'm going to not use a Pythagorean identity, although you could. I'm going to use this. The tangent of x is equal to the sine of x over the cosine of x. So, do I know the tangent of alpha? Please say yes.
Yes.
It's 3/4, right? Do I know the sine of alpha?
No.
Nope. Do I know the cosine of alpha?
Yes.
I do. Cosine is 4/5. So, if I need to cancel off the 4/5, I'm going to multiply this side by 4/5, and I'm going to multiply this side by 4/5. Cancel the 4's. That means that the sine of alpha is 3 over 5. And if you know the sine of alpha, you know what's the other one that's related to it? What's its reciprocal? Cosecant of alpha would be 5/3. There are all 5 of them. Sorry, all 6 of them. The 5 we didn't know. Okay, any questions? Okay, you have a bunch of problems on your assignment that are like this. Some of them are very simple, okay, like this one right here. It says, use the identities that we already know, the new ones that we introduced in this section, the odd and even identities, to simplify this. Sine of negative y is the same as the opposite of sine y. What's the answer? 0. End of story. Doesn't get any simpler than that. I'm going to write down the 1 sine alpha. I'm going to write this as 1. Careful here. I can pull that out front. This is the same as plus sine alpha. Now if I multiply these together, this isn't a difference of squares. This is a perfect trinomial square. So this makes 1 plus 2 sine alpha plus sine squared alpha. Now if you want to leave it that way, totally fine with me. I like everything in terms of one trig function. If you wanted to leave it this way, suppose that wouldn't be the end of the world. Okay, but I think that's what they're after in the back of the book. Okay, any questions there? Okay, 2 more real quick. Anybody recognize this? There's more than one way to do it, but I think the easiest way to do this would be, let's take out a negative. I don't really like working with negatives, so let's take that out. This is tangent squared of t plus 1 over secant squared of t. Does this look familiar? Flip your page over. Isn't tangent squared plus 1 a Pythagorean identity? Isn't that secant squared? So this is negative secant squared t over secant squared t. What can I do? Cancel that with that. And my final answer is -1. Okay? That's the type of stuff they're after. Thereafter, you rewriting things using the identities that you already know, and then simplifying. Okay, last one. Take a good look here. Now, if you see a sign to the fourth, okay, we don't have any identities with sign to the fourth in them. But do you notice anything about the two of these?
You do with signs.
They both deal with signs, and in fact, I've got 4 signs multiplied together here, 2 signs multiplied together here, so don't I have a common factor? So if I take out the sine squared of x, I'm left with sine squared of x minus 1 over secant of x. Does this part look familiar? If you've got a trig function squared, that's your clue that it's probably going to be, not always, but probably going to be a Pythagorean identity. Can I get something that looks like sine squared minus 1? It's close to cosine. So if I were to do this, remember we start with this. I need a minus 1, so let's switch places with the two of these. And what that would do is, we'd have a minus 1 on this side, I'd have a minus cosine squared on this side. So this is sine squared x. This is a negative cosine squared of x over secant. Thanks to Caitlin, I put that in parentheses. Okay, now, last thing we have to do here is, it would be nice if we could simplify this just a little bit further. Let's turn that into a 1 over cosine. So this is negative sine squared x cosine squared x over 1 over cosine x. And if I flip that over and I multiply, that puts the cosine x on the top. So here's what I've got. This is my final answer on this problem. Negative sine squared x cosine, how many cosines do I have? Cosine squared times cosine cubed x. There's our answer. Okay? Any questions? Stretches a different part of your brain when you're doing these types of problems. So you might get frustrated, but stick with it. If you need help, come and